Consider the primal dual pair of linear programming problems given by P and D shown here. And let B be a basis, and let N be the indices not in B. We're going to look at what a dual feasible tableau is. Recall that the tableau associated with B can be obtained from the system Z minus C transpose X equals 0, AX equals to B, by applying elementary operations until Z and the basic variables are pivot variables of the system. Let's take a look at an example to see what that means. So suppose that A is 1, 1, 1, 1, 2, minus 1. B is 0, 2. And C is 1, 2, 3. And suppose we are given the basis B equals 1, 3. To obtain the tableau associated with this basis, we start with this system. And transform it to a system that has Z, X1, and X3 as pivot variables. So we start off by subtracting the second equation from the third equation. So X1 minus X1 is 0. 2x2 minus x2 is x2. And negative x3 minus x3 is negative 2x3. And 2 minus 0 is 2. And we are going to divide the third equation by 2. That gives us 1/2 x2 minus x3 equals 1. And adding the third equation to the second equation, we get x1 plus 3/2 x2 equals 1. And multiplying the third equation by negative 1, we get minus 1/2 x plus x3 equals minus 1. And adding the second equation to the first equation, we get the following. And finally, adding 3 times the third equation to the first equation, we get this. So now Z, X1, and X3 are pivot variables. And so this is the tableau associated with the basis 1, 3. And symbolically, the tableau can be represented as follows. Z minus C sub n transpose minus Y star transpose A sub n times X sub n equals Y star transpose B and X sub B plus the inverse of A sub B times A sub n times X sub n equals the inverse of A sub B times B, where Y star is given by the transpose of C sub B transpose times the inverse of A sub B. Remember that A sub n is a submatrix of A formed by the columns of A indexed by the elements in n. And C sub n is simply the tuple obtained from C by taking only the entries indexed by n. Now, a dual feasible tableau is one such that this is non-negative. So, dual feasible if C sub n transpose minus Y star transpose A sub n is non-negative. But this can be rewritten as Y star transpose A sub j less than or equal to C sub j for all j in n. And now, since Y star satisfies this, That means y star transpose A sub B equals C sub B transpose. And what that means is y star satisfy all the constraints in the dual. And that's why it's called a dual feasible tableau. Because the y star that is obtained by computing this is a dual feasible solution. And also, the right-hand side value of the z row is the objective function value of y star. So if we look at the example over here, well, this is non-negative, right? So we are taking a negative of a non-negative number. And this is a dual feasible tableau. And this is going to be the objective function value for the dual solution that is implicit in this tableau. Now notice that we don't have an explicit description of y star here, but if you're going to compute y star using this formula, you actually get y star equals 2 minus 1. And you can check that the objective function value of this is indeed negative 2. Now, if this also happens to be non-negative, then this tableau tells us that the basic solution determined by B is a feasible solution to P. And since y star is also dual feasible, that tells us that the basic feasible solution determined by B is an optimal solution. And if we look at the example, we have a negative value for the basic variable x3. So the basic solution determined by B is not feasible. And so this is the interesting case when not every value here is non-negative. And since the dual problem is a maximization problem, and the dual feasible tableau implicitly carries a dual feasible solution, the question is whether we could iteratively increase the right-hand side value of the z row by going through dual feasible tableaus. And this iterative process is the essence of the dual simplex method.